Hey everyone, and welcome. Today we're diving headfirst into one of the biggest mysteries out there, the black hole. And to guide us, we're going to be looking at one of the best sci-fi movies ever made.
So let's start with the big question, the one that Interstellar left us all thinking about. Remember that climax? When Cooper just goes for it, plunging into the massive black hole Gargantua? What he sees in there is absolutely wild, but you gotta wonder, how real is it?
Okay, so that's going to be our central question for this whole explainer. We are going to break down the actual science and figure out what would really happen if someone took that insane leap of faith. So just to refresh your memory, what does the movie actually show us? Well, Cooper's fall starts out in total darkness. Then his ship gets hammered by these grain-like particles and flashes of fire. He has to eject, right? And then he ends up in this bizarre five-dimensional library thing, the Tesseract, where he can actually communicate with the past using gravity. It's an incredible scene for sure, but the real question is how much of that is legit science and how much is just, Hollywood?
Well, to even begin to answer that, we've got to rewind way back, like over 100 years ago, to a time before the words black hole even existed. And it all starts with one guy and his mind-bending ideas. Albert Einstein.
It's pretty amazing when you think about it. The whole journey from just a crazy idea on paper to something we could actually prove, that took over a century. It all kicked off with Einstein's theories of relativity back in the early 1900s. But the name black hole, that didn't really catch on until the late 60s. And we didn't get our first actual picture of one until 2019. It's just this incredible story of scientific patience and discovery.
Okay, so first up is Einstein's special theory of relativity, which he came up with in 1905. The main takeaway here, the big idea, is that your speed through space actually affects how you experience time. So imagine you're zipping through the cosmos in a spaceship near the speed of light. For you, time would literally tick by slower than it would for everyone you left behind on Earth. Wild, right?
All right, so 10 years later, Einstein drops an even bigger bombshell, his general theory of relativity. And this is the absolute key to understanding black holes, because it turns out it's not just speed that messes with time, gravity does too. A lot. Think back to that water planet in Interstellar, the one where every hour they spent there was 7 years back on the ship? That's it. That's gravitational time dilation, and it's all because of Gargantua's insane gravitational pull. So how does that even work? Well, Einstein came up with this brilliant way to visualize it. He said, imagine space and time are not separate things, but are woven together into one giant cosmic fabric. Now, if you take something massive, like a star or a planet, and put it on that fabric, what happens? It creates a dent, right? A curve. And according to Einstein, that curve, that bending of space-time, is what we feel as gravity.
And this idea, this fabric of space-time, leads to his most shocking conclusion. See, if gravity is just a bend in the fabric, then it doesn't just pull on things like spaceships or planets. It pulls on everything that travels through that fabric, including energy and, this is the big one, even light. And that led to this unbelievable theoretical possibility. What if an object was so massive, so incredibly dense, that it bent the fabric of spacetime so much that nothing could climb out of its gravity well? Not even light, the fastest thing in the universe. You'd have an object that was completely, totally black. So, Einstein gave us the what. He laid out the theory. But what about the how? Where do these cosmic monsters actually come from? Well, they're born from the death of the biggest, most massive stars in the entire universe. You can think of a massive star's life as this epic cosmic tug-of-war. On one side, you have nuclear fusion in its core, creating this enormous outward blast of energy. And on the other side, you have the star's own immense gravity trying to crush it inwards. For millions of years, they're in perfect balance. But eventually, the star starts to run out of fuel. The outward push gets weaker and weaker until it stops, and gravity wins. It wins in the most spectacular way possible. The star collapses in on itself and then explodes in what we call a supernova. And what's left behind is this super dense core. And if that core has enough mass, its gravity is so strong it becomes a black hole.
So what's the magic number? How massive does it have to be? Well, there's a specific cutoff point, and it's called the Chandrasekhar Limit. A star's core, the part that's left over after the supernova, has to be at least 1.4 times the mass of our sun. If it's bigger than that, it has enough gravitational oomph to collapse into a black hole. And hey, here's some good news for us. Our sun isn't even close to being that big, so no need to worry about Earth getting sucked into a black hole of our own making. Okay, so now we know what they are and how they're made, so let's do it. Let's get closer.
Let's pretend we're on a ship, just like Cooper, approaching a monster like Gargantua. What are we going to see?
So as we're getting closer, three main things are going to stand out. First, you can't miss the accretion disk. That's that incredibly bright, super hot ring of gas and cosmic junk spinning around it like a crazy cosmic frisbee. Then, as we get even closer, we'd hit the photosphere. This place is just mind-boggling. It's where light itself, photons, can get trapped in orbit. And finally, the big one, the one everyone knows, the event horizon, the ultimate point of no return.
Now, Interstellar showed us this beautiful, glowing orange ring for its accretion disk. And while it looked amazing, the reality is a little different. See, that disk is so insanely hot from all the friction and gravity that it mostly shines in X-rays, which we can't see with our own eyes. So any colors you see in artist renderings are really just to help us visualize it. Oh, and another cool detail. You know how in real pictures one side always looks way brighter? That's not an accident. That's the side that's spinning towards us. The light from it gets kind of bunched up and boosted, an effect they call Doppler beaming.
Okay. Deep breath. We're here. We're at the edge, the point of no return. So, let's do what Cooper did. Let's take the plunge. Let's cross the event horizon and see what's on the other side.
Now, I gotta be really clear about something here. This is the exact point where science stops and speculation begins. Everything we're about to talk about is based on math and theory, not on something we've actually seen. Nobody has ever seen inside an event horizon. It's one of the biggest mysteries in all of physics, which is exactly why a movie like Interstellar had to get a little creative.
So, what does the math say is in there? Well, according to Einstein's general relativity, at the very center of a black hole is something called a singularity. It's a single point where the fabric of space-time gets stretched and curved to infinity. Density becomes infinite. The pull of gravity becomes infinite. It's a place where all the laws of physics as we know them just stop working. They completely break down. So yeah, forget about that five-dimensional library. The scientific reality is a lot less cinematic. The consensus is pretty clear. If you or your spaceship crossed the event horizon, the gravitational forces would be so extreme that they'd stretch you out like a piece of spaghetti. They even have a name for it, spaghettification. Seriously. You'd be torn apart atom by atom in milliseconds. It's just instant, total disintegration.
You know, after hearing that, it's really easy to just think of black holes as these evil, destructive monsters. But that's a huge misunderstanding. So let's kind of reframe how we see them and what they actually do in the universe.
So, the myth, right, the thing everyone thinks, is that black holes are just cosmic vacuum cleaners, roaming around sucking everything up. But the reality is so much cooler. They're actually galactic anchors. They're the gravitational center that entire galaxies with billions of stars orbit around safely and predictably, just like planets orbit the sun. So they're not forces of chaos at all. They're actually fundamental to holding galaxies together.
And I'm not talking about some galaxy far, far away. This is happening right here, at home. Our galaxy, the Milky Way, is currently spinning around a supermassive black hole at its center. It's called Sagittarius A star, and it's the anchor that holds our entire galaxy together.
There's this great quote that I think sums it up perfectly. It says, "If you maintain a proper distance from a black hole, if you maintain social distancing, you will be safe and secure." And that's really it. They aren't predators hunting you down. They're just incredibly powerful, but also predictable. As long as you keep your distance, you're totally safe.
So there you have it. We've gone from a Hollywood blockbuster all the way to the very edge of physics. We've learned that black holes probably aren't secret portals to the past, but they are these incredible cosmic anchors. But I want to leave you with one last thought, and it's a real brain melter. We know that gravity slows down time, and we know that at the singularity, gravity is infinite. So what does it even mean for time to slow down